Hi guys, my name is Nikki, and today I'm going to be talking about dipoles. I'm going to be reviewing both bond dipoles and net dipoles and giving a few examples to illustrate my points. First things first, you can find the info on dipoles on page 13 in chapter 1 in the course reader. So what is a dipole? Basically, a dipole is any sort of charge difference in a bond, and as we'll see later on with net dipole moments, in any molecule. It only occurs in heteronuclear covalent bonds. Heteronuclear just means that the two nuclei involved are from two different elements. For example, C and Cl. So a dipole moment is represented by this funky-looking M-like thing called mu, and is equal to the charge on the atoms times the distance between them. I don't think we need to know this for the final, but just in case, here it is. Okay, so we draw a dipole moment with an arrow pointing toward the region of negative charge. I'll explain that in a moment in my example, but for now just memorize that it points toward the more negative side. Okay, so what causes a dipole moment? Just to be clear, right now I'm just talking about bond dipoles, not net dipole. So a bond dipole is caused by a difference in electronegativity between two nuclei, which results in them pulling on the electrons differently. Since the electrons are not shared equally, the bond becomes more ionic in character. Let's use H2O as an example. H2O has two OH bonds. There's a large difference in electronegativity of O and the electronegativity of H. O has an electronegativity of 3.5 and H has an electronegativity of only 2.1. But because of this difference in pulling power, the electrons are pulled away from the H and toward the O, leading to the O becoming partially negatively charged and the H becoming positively charged. So when we're drawing the dipole moment, we draw the arrow in the direction that the electrons are being pulled. An easy way to remember this is that the side that loses the electrons has what looks like a plus, so it is positive, and the other side is negative. So that was the basics of a bond dipole. It's caused by differences in electronegativity, resulting in an unequal sharing of electrons and partial charges. Now let's talk about bond dipoles versus net dipoles. So typically, you're going to be given some sort of molecule and asked whether it's polar or not. You basically have three options. If the bonds themselves are nonpolar, there is no chance of there being any polarity in the molecule, so the molecule itself is nonpolar. But if the bonds are polar, they can either cancel out and have no net dipole, resulting in a nonpolar molecule, or they cannot cancel, which results in a net dipole, and the molecule is polar. Canceling out is basically dependent on the geometry of the molecule, which I'll explain in the next example. Let's look at CH4 and CH3Cl. Both have polar bonds, but only CH3Cl is polar. A molecule is only nonpolar if the sum of the bond dipoles, which is called a net dipole moment, is 0. The thing to remember is that polar bonds cancel out if they are situated 180 degrees apart, basically if they are opposite each other. Now CH4 doesn't look like it should be nonpolar, but if you go through the vectors and actually draw out all of the bond dipoles, they cancel out, resulting in a net dipole of 0, and thus a nonpolar molecule. CH3Cl has the same geometry as CH4, but is polar because the bond dipole for the CH bond doesn't completely cancel out the other bond dipoles. Let's talk about cis and trans. A good way to remember the difference between the two is to think that the Transcontinental Railroad went across America. So trans means across, while cis is the same side. Let's look at dichloroethylene to better understand this. In cis dichloroethylene, the two Cl's are on one side, and the H's are on the other side of the carbon atoms. If you draw the bond dipoles for each heteronuclear bond, you'll see that all of them point downward, since C is more electronegative than H, and Cl is more electronegative than C. However, if you look at trans-dichloroethylene, the two CH bonds are 180 degrees apart, so they cancel, and the two Cl-C bonds do the same. All of the bond dipoles cancel, so there is no net dipole moment, and the trans-dichloroethylene is nonpolar. An easy way to remember this is to look at the molecular structure in terms of VSEPR theory. If there are no lone electron pairs, or the lone electron pairs cancel, aka they are 180 degrees apart, and the bonds involved are all of the same type, the molecule is nonpolar. However, if there are multiple types of bonds involved, or anything else that doesn't fit this situation, then draw out the bond dipoles and add them together. If the sum is 0, then there is no net dipole moment, and the molecule is nonpolar. I hope this helped in terms of explaining dipole moments. Let me know if there's any other things that I should cover. Thanks, and good luck studying!